Yo, hello guys. Hope you're doing well. Today we're going to be solving a physical science paper 2 or chemistry question in preparation for our September prelim preparatory exams, whatever you want to call it. So we're going to be doing acids and bases, and specifically I want to talk about the type of questions where you have two reactions or a back titration type reactions. I'll also obviously be covering all the questions that lead up to such a question. As you might have noticed, since you've been in the education system for quite some time, there are normally these questions that I like to call warm-up questions. So we'll also talk about that, how to deal with those type of questions and different ways in which those questions come in. I got this question paper from stanmorephysics.com. You can always use that website, or if you have your own preferred website, look, I'm not here to impede on that. And it's KZN paper from last year's prelims. Let's start. So acid-based questions are normally questions, 7 questions. And as I said, they normally start with the boring stuff. They normally start with the vanilla stuff where we're talking about what's an acid, what's a base. Maybe they ask you for the Arrhenius definition. In this question paper, they ask what's an ampholyte. Sometimes they do the conjugate acid-base type questions. They ask you what's the definition of a strong acid, so on and so forth. Then you'd be calculating pH, and then we'd move on to the titration question. And in this case, the two reaction questions. So that's normally the progression of this type of questions. And I'll give you some minutes to read over it. You can pause the video, look over it, even try to solve it by yourself, and then we can get going. Okay, I'm going to start now. The first question, 7.1, it says consider the following reaction. We have sulfuric acid acting with water to give us the sulfuric acid anion, HSO4 minus, plus H3O, which can also exist as H plus. Both of these stuff are anonymous. They mean the same thing. The first question, 7.1.1, asks us to define an ampholyte. We know an ampholyte to be something or a species that can act both as an acid or base. We'll say it's a substance. So a substance that can act as an acid or base. This is the formal definition. Look, I hope your teachers are at least providing you with some resources, your definition resources that include every definition that you might be asked about. If you don't have that from your teachers, look, don't blame them. You can just tap in and go on the internet and search for one. Just type in definitions, chemistry, NSC definitions for chemistry, or DBE definitions for chemistry. Or even if you are IEB student, you can also find that as well. So that's the first definition. You got 2 marks in the bag. We move on to the second question. Apart from H2O, which substance in the above equation can act as an ampholyte? So what qualifies something to act as an ampholyte? Let's actually put some flesh into this definition that we did in 7.1.1. When we say that it's a substance that can act as an acid or a base, what we really mean is that it's something that can give a hydrogen, it can give a H, and if we say it acts as a base, it can also receive an H. So we need to look for something, a species in our reaction, a substance in our reaction that can do both. It can receive an H and give an H. Let's go through them quite quickly and see which ones can do so. It says obviously other than water. We know that water is an ampholyte. It's one of the most famous ampholytes because we say it can go both ways. It can receive an H and become H3O. It can give an H away and become OH minus. So we know that this is the most famous ampholyte. Another ampholyte that can receive one more H and give off an H. So it can act both as an acid, a base and acid, because I said receive first and then give. So it can act as a base or an acid. Let's see who else lives up to that test. We can see that it would not be this. H3O would not become H4O2 plus. That doesn't exist. That will never exist. And it can't, it can give off one. I mean, it has an extra one. So it can give off one and become H2O. So this does exist, this doesn't exist. So it's not an ampholyte. Let's look at H2SO4. H2SO4 can give off one. So it can be an acid and give off. When it gives off one, it would be HSO4 minus as it appears over here. Can it take one more in? Can it receive an H as a base would? No, we have never ever seen H3SO4 1 plus. In fact, we have seen H3PO4, so don't confuse it with H3PO4. That is something that exists. That's another polyprotic acid. Polyprotic meaning that it can give more than one H or give more than one H. So we've seen that before, but we know that, look, this doesn't exist. This looks like something out of a fantasy movie. So that leaves us with the last character, last substance in our equation, with that being HSO4 minus, or the conjugate base. Yeah, the conjugate base of H2SO4. This can exist both as an acid or base. It has room to give off one more. It can give off one more H and exist as SO4 2 minus. It can add one more H and exist back as it used to, H2SO4. So that, apart from H2O or water, the other substance that can exist or act as an ampholyte would be HSO4 minus. You can go through this whole process of elimination like I did here. But look, if you don't want to do that and you know what the answer is straight off the bat, it saves a lot of time. So I'm just talking through it. You can, however, do this process of elimination very quickly in your head. And you'd find out how it looks. Okay, let's move on. Now we're going to move on to question 7.2. So this was 7.1. We'll move on to question 7.2. And we are still in the safe zone or the safe realms. We're still doing the nice, easy stuff. But as you can tell, even though this is a 2-mark, 1-mark question, and the next question is a 3-mark question, I'm going into detail so that we have a nice comprehensive solution, so that you understand how we get to the answers that we do. So if any questions similar to this come about, you know the thought process. 7.2.1, it says, or 7.2, a solution of hydrochloric acid, it has a concentration of 0.1 moles per decimeter. Let's talk about a few things here, just from this one phrase or sentence. The first thing, they talk to us about hydrochloric acid. Hydrochloric acid is something that we know historically it is a strong acid. Let's talk about what the definition of that is. A strong acid is an acid that dissociates completely in solution, and that solution is normally water. So when we say it dissociates completely, fully, what we mean is that it looks something like this. If I put HCl in water, in a solution, it would dissociate or deionize to become its separate ions like this. And it would stay like this. Once it dissociates, once they separate, once they divorce, they stay like that. But a weak acid, on the other hand, is something that does not dissociate completely. So it's the exact opposite of a strong acid. So it would mean that, look, it says something like acatic acid, CH3COOH. That's a weak acid that we know. Why is it a weak acid? Because it does not dissociate completely. If I put acatic acid into water, into a solution, it would deionize. So it would exist as this CH3COO minus plus H plus. But look, they don't want to stay divorced. Some particles or some molecules of acatic acid will remain like this, while some of them would stay in its former form like this. So they're a bit undecided. Some of them would like to stay divorced, but some of them, look, they want to get back together, see if they can work things out, go for marriage therapy or some. I don't know anything about this, but it's things I see on television, right? So I hope with this analogy you can understand the difference between a strong acid and a weak acid. Now this here is what we're going to use to be able to get the pH of our solution. How are we going to do that? We understand that when things dissociate, when it's a acid or base, if they do dissociate, if they are in solution, we can use this concentration and use this, what do you call this? This concept of concentration ratio. I would like to restrict this normally to dissociation type questions for acid and base. We normally know mole ratio, but you can use concentration ratio here as well. So I'll talk about how we do that because that's the way in which we solve the question. From this first phrase, I was able to explain what is a strong acid, how it dissociates, what is a weak acid, what makes it a weak acid, and how we're going to use concentration ratios. We know of mole ratios, but we can also use concentration ratios. So they ask us to calculate the pH of this hydrochloric acid solution. To do this, let's first write out our dissociation reaction. We're going to say that it dissociates. Remember, you can write H3O plus or you can write H plus. So H3O and Cl minus. So it dissociates like that. It dissociates completely. So I can imagine that all of my HCl becomes this and this. So there's nothing of this left anymore. That's the definition. Now let's look at our formula. If you go to the back of your paper, when you write in your paper, you'll see that you can find pH by saying negative log H3O, the concentration of H3O. Now here comes what we're talking about. We can use our concentration ratio between HCl and H3O. That ratio is 1:1. And so we can see the concentration of H3O is equal to the concentration of HCl, which happens to be 0.1 moles per decimeter cube, as given in the question. Now it's quite simple. Let's just substitute this into our formula. pH is equal to negative log 0.1, and then because log is to base 10, so 0.1 to base 10. I believe it will be 1, but you will check. We'll check. I know when you write exams anyway, you even put 2 plus 2 in your calculator. So let's be careful. Yes, it is 1. And this checks out with what we do know about HCl. It's a very strong acid. It normally has a pH of 1. So yeah, this does check out. Now, let's talk about alternative questions that might arise from this same thing. Maybe they tell us there's a solution of H2SO4, and it has a concentration again of, let's say 0.1. Once again, 0.1 mole per decimeter cube. How would you do the same thing? Again, we're going to start with that dissociation. H2SO4 would dissociate into SO4, 2 minus, that is our anion, plus 2H plus. Why? Because we have to balance it. So you'd start by saying SO4 2 minus plus H plus, but you'd see that I have 2H, so I have to balance that here as well. So that's how that would differ. This is for a polyprotic acid. You can imagine if this was H3PO4, what's this called? Phosphoric acid, it would do the same thing. You would say H plus plus PO4 3 minus, and then you'd say, okay, this has to be 3 because I have to balance this and this. How do I know the anions and cation numbers? It's simple. This 3 comes from here. It used to be here. And this invisible 1 that's here, because this is a, I forgot what you call these things. Anyway, this 1 that's over here used to come from this cation. Anyway, yes, so this is how you dissociate it. And then again, you're going to use your ratio. So the ratio of H2SO4 to H plus is going to be 1 to 2. And so if you have 0.1 here, it would be 0.2 over here. So your concentration of H plus or H3O plus would be 0.2, and then you can find your pH the way you would here, and that would be 2. So I hope this makes sense for you. To find the pH, you're first going to use dissociation, then find the ratio of your whole molecule to your H plus or H3O, then find out the concentration of your H3O and put it into the formula. Let's move on quickly. To the next part of the question. A flask contains, and this is, now we're coming to the cursed question. We want to know, firstly, do you even know that this is a cursed question? If you do know that this is a cursed question, look, I'm here to tell you that's the first part of the problem solved. I don't know, in TV and film, we normally hear people say the first part, cure, is acknowledging the problem, some nonsense like that. So it's the same thing here. The fact that you can see that this question is difficult and you know why it's difficult, that's the first part. Let's first find out why it is difficult by reading over the question. A flask contains, and I'm going to break it down after this first reading. A flask contains 200 centimeter cube of an aqueous solution of sodium hydroxide of concentration 0.1 moles per decimeter cube. To this flask, 50 centimeter cube of an aqueous solution of barium hydroxide of unknown concentration is added, giving a total volume of 250 centimeter cube. In a titration, 20 centimeter cube of this mixture is completely neutralized by a 30 centimeter cube of a hydrochloric acid solution of concentration 0.1 moles per decimeter cube. The ionic reaction is represented by the following equation. So firstly, what makes this question cursed after this first reading is that there's a lot of information to digest. And secondly, what makes this question doubly cursed is that it has two different reactions. So there's two different reactions. There's a lot of information to process. And the third thing, in my first reaction, I have two sources of OH. So that's another problem. I have two sources of OH. We'll talk about why that's a problem later. Another thing also that makes this question difficult is that from the 250, I'm only taking 20. So that's also another problem. Now, for the first reaction, this one over here, we're going to do it in this purple. And for this second reaction over here, we're going to do it in green so that we differentiate properly. So let's break down what is happening in the first part. Let me first copy this page. It's like I'm going to do a lot more of these. Okay. So let's highlight what we have and try to keep score of what we have been given. We have 200 centimeter cube of NaOH and it has a concentration of this. So let's talk about what we have in the first reaction of NaOH. We write down what we have. For this type of questions, you have to write down what you have because, look, it can be a bit too daunting. You're not going to remember everything. The volume, so for NaOH, we have the volume. This is 200 centimeter cube. We want the required SI unit is supposed to be decimeter cube. How do you convert from decimeter cube to centimeter cube to decimeter cube? It's quite easy. You're gonna just divide by 1,000. So let's carry on again. We have that if we divide by 1,000, we're going to get 0.2 decimeters cubed. We then move on. We have the concentration. That's also something that's given. We have the concentration, and that is 0.1 moles per decimeter cube. Because we have these two things, we have C and V, that gives us an indication that we're going to use this formula. We're going to use C is equal to N over V. And we're going to find our moles. So the first indication I get from here is, look, I can find the moles of NaOH. Hey. And we know if we can find the moles, as is always the case in stoichiometry, if you can find the moles, then everything becomes a lot easier. Then you can move around and use mole ratios here and there and whatever. Let's talk about what's known in BaOH, or barium hydroxide. What's known in barium hydroxide, it says to that flask that has 200, this flask here of 200 centimeter cube, we're going to add 50 of barium hydroxide. So the volume of barium hydroxide is 50. Again, it is saying when you add these two to make that mixture, that NaOH plus BaOH mixture, the volume of this mixture is the addition of those individual volumes. So it will be 250. Again, this is something that we can convert. When we do convert it, we're going to get 0.05 decimeter cube. Divide by 1,000. I don't know the concentration, so I obviously cannot find this. I can't find the what do you call this, the moles of barium hydroxide. I can't find it because I don't know 2 out of 3 of what's required for me to know. However, I do know that when I add both of these volumes, 250, I get a volume of the mixture 250 centimeter cubed. And again, we can convert this to into decimeter. So that's what we know about the first reaction. Let's see what we know about the second reaction. If we come down to the second reaction, it says this is a titration. In a titration, 20 centimeter cube of this mixture is completely neutralized. Okay, let's start there first. So in the second reaction, I have this mixture here. So this is the first reaction. In the second reaction, I have this mixture of NaOH and BaOH. We say that we have a volume of 20 centimeters. So from that 250, we take 20 centimeter cube. Remember, convert this as always 0.02 decimeter cube. And they say that this, and that's all we have. We don't have the concentration for it. We don't have the moles for it. And after that, it says that this is neutralized. So that word neutralized is of the most importance. In fact, it's probably the most important thing here. So when we say that it's neutralized, we know that the pH, firstly, for something that's neutral is 7. And when it's neutralized, we know that all reactants are used up. So there's no reactants left. All of the reactants are used up. So those are the two things we gather from just that word neutralized. They say it's neutralized by what? So this NaOH and BaOH, because it has OH, we can think of it as our base in this titration. So let's look at what's given of the acid. It says neutralized by 30 centimeter cube hydrochloric acid solution. So hydrochloric acid, we see it has a volume of 30 centimeter cube, and this is 0.03 decimeter cube, and it has a concentration of 0.1. I think it's 0.1. It's a very common number, I see. So 0.1 moles per decimeter cube. They also give us the ionic equation, and this helps us understand further that it is a neutralization reaction. If you are familiar with neutralization reactions, you know that it's acid plus base equals water. So one of the things you learn in grade 10 when you go through types of acid-base reactions, like neutralization looks like this. So let's carry on now. Now, for us to deal with these sort of questions, because I want to give you a general solution, I want to give you a general method of how to deal with this type of reactions. Write out what's given in your first, write down what's given in your second, and then you will see clearly what you have to do. You will start with the second reaction. You will start with the reaction that is neutralized or that has everything known. Why? Because you're going to see now that there's a common point. Between the first and second reaction, there's a common point. There's a common species. So in the first and the second reactant, I know that I have that NaOH, BaOH reactant in both of them. One is a product and one is a reactant. So what we're going to try to do is to use this to get the moles of this. Once we get the moles of this, then we're going to do dilution. Hey, it's a lot. Then we're going to have to use this formula, because why am I using this formula? C1V1 is equal to C2V2. Why am I using this formula? Because you use this formula when you have a smaller volume taken out of a bigger volume. So you can imagine we had that NaOH, BaOH mixture like this. And then maybe we took a pipette or something, and then we took a small percentage of this to put it into that other flask, so that we can have us put that HCl so that it would neutralize. So this is what happens. Whenever you are taking a smaller volume from a bigger volume, you will always use C1V1 is equal to C2V2. So we're going to use this formula over here. We're going to use this formula to be able to go backwards and see what we can do. So as I said, we're going to use this to find the moles. We find the moles from here. We use mole ratio to get the moles of this. After we get the moles of this, then we're going to use that C1V1 to move here. After we move here, because now we have the concentration here, we can find the moles here, and then use the moles to find this, use the moles to find this. But we can already get these moles as well. I hope this makes sense to you. Let's actually go for it and see how we fare. So, let me bring that question. Right. So the first question, 7.2.2, it asks, what is the pH of the solution when the end point of the titration is reached? We talked about this. It was that word neutralized that gives us a clue to this. So 7.2.2. It says choose from less than 7, equal to 7, or greater than 7. The answer is equal to 7. You get your 1 mark there. Now, if they asked you to give a reason for this, then you would say it's equal to 7 because this is a neutralization reaction. That's it. The word neutralize tells us it's a neutralization reaction. 7.2.3, now we're getting to the big boys. Calculate the number of moles of hydroxide ions present in the 20 centimeter cube of the mixture of sodium hydroxide and barium hydroxide solution. So they're talking about this guy here. They say find out the moles of this here mixture, that NaOH plus BaOH mixture. Find out the moles of hydroxide ions. Yeah, I'm going to have to work and find out what is that going to be. So let's start solving now. Let me delete this. Put this up here. So if they are talking about this second equation here, we're going to deal with the second equation. So to do this, we're going to say, and this is for question 7.2.3, we are going to, as I said before, use our HCl to find the moles of HCl. So we're going to say C is equal to N over V. And this is for HCl. Our concentration of our HCl is 0.1 moles per decimeter cube. We want to find the moles of HCl, and the volume of HCl is 0.03. So when we multiply this, we're going to get, we're going to get exactly the same thing. So the moles of HCl is equal to 0.03 as well. 0.3. Wouldn't it be 0.003? Let me see. Yeah, it would be 0.003. So 0.003 moles. After that, as I was saying before, since we now know the moles of HCl, we're going to use the mole ratio between HCl and this mixture of NaOH, BOH. So we're going to say next after this, what is the ratio of HCl to that mixture of NaOH plus BaOH? Now you might get confused when I write it down like this, because then you're going to see I don't really see the ratio. But this ionic equation here, it tells us the ratio is 1 to 1. So we're going to use, we're going to be using this ionic reaction. Let's not use this because you're going to get more confused. So we want to know what is the ratio between H3O and OH minus. We know that our mixture of barium hydroxide and NaOH, that is our source of OH, and HCl is our source of H3O. So when we do it like this, we can see it's a 1-to-1 ratio using this reaction over here, that ionic reaction of what's happening. And so we can see it's going to be the same. So the moles of OH are going to be equal to the moles of H3O. And the moles of H3O is 0.03. Again, why is it 0.03? Because of dissociation. And we know that the mole ratio between H3O and HCl is also 1 to 1. So it's the same thing here as well. So we move from here to here to here. So we've solved the first question. We have found the moles of HCl and used the mole ratio of H3O to OH to find the moles of OH. We calculated the number of moles of hydroxide ions present in that 20 centimeter cube of the mixture. So we've done that. Now, let's move on to the next question. 7.2.4. Calculate the initial concentration of barium hydroxide, BaOH, to solution that was added to the solution of sodium hydroxide. So they're saying before even the first reaction begins, we want to know what is this unknown concentration. That's what they're asking us for. What is this unknown concentration? So to work our way up there, let's see where we are in terms of the steps. We have done this. We now know the moles here. After that, I said we're going to have to use the C1V1, C2V2, because these are both the same thing, but just in different volumes. We're going to have to use that and then get to where we want to in here or here by using mole ratios. So that's our how we're going to progress. So we say that we know the amount of OH in this 20 centimeter, but we want to know the amount of OH in the 250 centimeter thing. So let's work our way up there. I want to know the concentration there. So I'm going to say C1V1 is equal to C2V2. Let's take 2 as the 250 centimeter cube solution and 1 as the 20 centimeter cube solution. So we know the concentration, we can find the concentration of OH. We can find C1. So C1 would be equal to N over V, right? And let's substitute what we have here because we want to find C1. OH, the moles of OH, 0.003. And the volume of our barium hydroxide, this was 20 centimeter cube, so it would be 0.02. Let's find out what that gives us. 0.003 divided by 0.02. We get a concentration of 0.15 moles per decimeter cube. So we're going to substitute it back here. And we're going to say for C1, for the 20 centimeter cube solution, I have a concentration of 0.15. My volume is 0.02, that's 20 centimeters. And for C2, I don't know what C2 is. I'm trying to find what was the concentration before I took it out of the, when it was in the 250 centimeter cube solution. So that's C2, and the volume of C2 is 250 centimeters or 0.25. So from here, you put that in your calculator, you divide both sides by 0.25, and we're gonna get, what is this now? Hey, man. 0.15 times 0.02 divided by 0.25. Okay. We get 0.012. That's what I'm getting. 0.012 moles per decimeter cube. So this is the concentration in that 250 centimeter solution. It's that concentration in the first part of the reaction before we took it out to make that 20 centimeter cube. Now from here, since we have the concentration, we can find out the moles here. So before we find out the moles, let's make something clear. This C2 is the concentration of OH in both NaOH and in BOH. It's the OH total. This is the total OH. So we can find out, let's find out the moles of the total OH now. So this is a 250 centimeter solution. And so we'll say for the concentration of OH total, that is equal to the moles of OH total over the volume that we talked about. When we substitute what we have here, we're going to say this is 0.012 is equal to this, which is what we want to find, the moles of OH total. And this is going to be equal to the volume, which is 250 centimeter cube or 0.25 decimeter cube. We are then going to find out what is N, the moles of the total OH. 0.012 times 0.25, we get 0.003 or 3 times 10 to the negative 3 moles. So this is the total OH. The total OH, guys, can be separated into two sources of OH. We said we have two sources of OH. Some of the OH exist as NaOH. Some of the OH exist as BaOH2, or barium hydroxide. So there are two sources of OH. If we add these two sources of OH, then we will get our total. So let's go and work through that. We can see over here in the first reaction that we have the ingredients needed to find out the moles of NaOH. So let's go ahead and do that. So to find the moles of NaOH, I can use again C is equal to N over V. What do I have there? 0.1 and 0.2 for volume. This is equal to the moles of NaOH is going to be equal to 0.1 times 0.2. I get 0.02 moles. Remember that it's also a base, so it can also dissociate into NaOH, Na plus OH minus. And I can see the ratio from this to this is 1. So the moles of OH in NaOH is also equal to 0.02 moles. We do the same thing or a similar thing for what we've been given of BaOH, but we don't need to do, we actually don't need to do all of this. I don't know why I'm getting too extra. We don't need to do all of this. Let me go back, because they want us to find the concentration of barium hydroxide, not of just the hydroxide in barium hydroxide. So we don't need to do all of this. Let's just write down the equation I was saying. So the moles total is equal to the moles NaOH plus the moles of BaOH. We found the moles of NaOH from my previous solution to be 0.02. And so we can use this to solve our question. So the total is, what did we get? So this is going to be 0.002. 0.002. And our total is 0.03. Our NaOH is 0.002 plus BaOH, or barium hydroxide. So our moles of barium hydroxide, when we solve for it by subtracting the total from NaOH, we get this is 0.01 moles of BaOH. After this, now we can find the concentration of BaOH, because that's what we wanted from the start. N over V. What is the volume of BaOH? It is 50 centimeter cube, or 0.05 decimeter. We can now find what we need here. It's going to be 0.001 divided by 0.05. Yeah, 0.05. And then when we put that in a calculator, 1 times 0.05, we get a concentration of 0.02 moles per decimeter cube. So let's review what was done. What we first did for 7.2.3 was we found out the amount of hydroxide ions present in 20 centimeter cube from the second equation by using the moles from this HCl that's given. We use these moles, use the mole ratio to find the OH here by using this here reaction. Don't look at this. Using this reaction. After that, we wanted to find, if we know what the concentration is in 20 centimeters, but we want to know what the concentration is in 250. So this is where we use the C1V1, C2V2 dilution, the dilution type of equation. When we did this, we found out what's the concentration of OH in the 250 centimeter cube solution. After that, in 7.2.4, we carried on and said, look, I'm going to now find the moles of that OH. After I find the moles of OH, I will say that this is the OH total because this is the OH that is found in both barium hydroxide and sodium hydroxide. Now I know that the OH that's found in barium hydroxide and sodium hydroxide is equal to the moles of sodium hydroxide plus the moles of barium hydroxide. So I know this, I could find this by using what's been given to me of C and V to find the N, and then I can subtract them to find out what's the moles of BaOH. After that, look, you're just going to use the formula C is equal to N over V to find out your concentration, which is the question here. So I hope that this makes sense to you. Any more questions, look, put it in the comments, email me. There's what's this? Yeah, I'm tired. My email is in the channel page. Email me any questions that you have and I'll try to get to it as soon as I can. Have a nice day, guys.